Before we begin tonight, I want you to do something small. Look around the room you're in right now. Whatever you see, the ceiling, the window, the light coming under a door, all of it exists because of something that happened 66 million years ago. Something violent, something total, something that ended one world completely and started another. Tonight, we're going to that other world, the one that came after the dinosaurs, the one that nobody really talks about. Before we go, tell me where in the world you're listening from tonight and what time it is. I genuinely love knowing where these late night explorers are. Drop it in the comments before you fall asleep. Now, let's go back. Opening. There is a moment in every extinction when the last one dies, not the last of a generation, not the last of a decade, the last of an entire way of life. And on one specific afternoon, the science is that precise now 66 million years ago, somewhere in what we would later call North America, the last non-avian dinosaur took its final breath. We don't know which species it was. We don't know if it was alone. We don't know if anything witnessed it. But we know the world that followed. We know the silence that came after the fire. We know the slow, strange, extraordinary story of what happened to the earth when the giants were finally gone. And that story, 66 million years of it, is what the night is about. The thing that always strikes me about the end of the dinosaurs is not the drama of the impact itself. It's the aftermath, the silence, the darkness, the 2 million years that followed, where the sky was dark, the forests were ash, the oceans were acid, and yet something was alive. Something small, something warm, something hiding underground and under roots and in the cracks of a broken world, waiting that something was us. Not us exactly, not yet, but our ancestors, the tiny, shrew-like, scurrying little mammals who had spent 100 million years living in the margins of the dinosaur world, in the shadows, underground, at night, always small, always careful, always, in some very real sense, afraid. And then one day the sky fell, and the giants were gone, and the earth was theirs. What they did with it over 66 million years is the story I want to tell you tonight. A story of strange animals you've never heard of climates so different from ours that the same planet would seem alien, of forests where Antarctica used to be, of seas where the Sahara is, of creatures that make our modern world look small and timid, of the long, patient, magnificent rebuilding of everything that eventually produced the world you're lying in right now. The last day, 66 million years ago, the Chicxulub impact. Let me take you to that last day, not to dwell in the catastrophe, but to understand where the story begins. Because every story needs its starting point, and this one begins with fire from the sky. It was a Tuesday, or something like a Tuesday. We can't know the day of the week. The concept didn't exist, but we can know the approximate time of year. The isotopic evidence from the rocks at Chicxulub suggests the asteroid struck in spring, specifically late spring in the northern hemisphere, which means the northern hemisphere was in bloom, flowers opening, birds, the avian dinosaurs nesting, the last non-avian dinosaurs of North America moving through a landscape full of life, unaware, as all of life always is, of what is coming. The object itself was approximately 10 to 15 kilometers wide. To put that in perspective, Manhattan Island is about 21 kilometers long. So imagine something slightly smaller than Manhattan, made of rock and metal, traveling at 20 kilometers per second. That is 72,000 kilometers per hour. That is fast enough to cross the entire diameter of the Earth in about 18 minutes. It hit the shallow sea off what is now the Yucatan Peninsula of Mexico, and what happened next happened faster than any living thing could perceive. In the first second, the asteroid vaporized itself and the rock beneath it, and a column of superheated rock and gas shot upward through the atmosphere. In the first minute, a fireball the size of a continent formed at the impact site. In the first hour, ejecta molten droplets of rock thrown upward by the impact fell back through the atmosphere as a global rain of fire. The friction of all that debris re entering the atmosphere heated the air itself, not just near the impact, everywhere. For perhaps 30 minutes to a few hours, anything on the surface of the earth that could burn, burned. Forests caught fire, grasslands caught fire. Even the air itself became briefly, searingly hot. A heat pulse, global, lasting hours. Then the cold came. The same debris that had rained fire now blocked the sun. Sulfur dioxide from the impact from the evaporated seabed, which was rich in sulfur, combined with water vapor to form sulfuric acid aerosols in the stratosphere. The sun dimmed, then nearly disappeared. Photosynthesis slowed, then essentially stopped. For years, perhaps a decade, the world went dark and cold and quiet. This is the world our ancestors survived. This is the starting point of the Cenozoic era, not with a bang, with a long, dark, freezing silence. The survivors who made it through, not the large things. Size was a death sentence in a world with no food. If you were big, you needed a lot of calories, and calories were gone. If you were small, you needed fewer. If you could eat insects which survived in enormous quantities, feeding on the dead, you had food. If you could burrow underground where temperatures were more stable, you had shelter. If you could eat seeds which had shells and could survive the darkness, you had a future. The small, burrowing, insectivorous, omnivorous mammals passed through, hungry, frightened, in a world that had just been comprehensively destroyed, but alive. Birds survived, not all of them. Many avian dinosaur lineages went extinct too. But the ancestors of modern birds made it through, probably the ground nesting, seed eating ones who could weather the darkness by living on stored seeds and insects. Crocodilians survived. They had been around since before the dinosaurs and they were extraordinarily resistant, could go months without eating, had respiratory systems that could function in low oxygen, highly acidic conditions. Turtles, lizards, snakes, fish in certain environments. And the mammals, the small, warm-blooded, quick metabolizing mammals, who could regulate their own temperature, who could survive in burrows, who would inherit everything. The Paleocene, 66 to 56 million years ago, the world rebuilds. The Paleocene, the first epoch of the Cenozoic era, lasting from 66 to 56 million years ago, 10 million years, the longest 10 million years in the story of mammals, the most transformative, the most strange. Imagine walking into a forest 60 million years ago. You would recognize the trees. Flowering plants, angiosperms had diversified enormously during the Cretaceous, and they survived the impact better than the conifers, so the post-impact forests were full of flowering trees, figs, palms, early relatives of plants, we know, but the animals would be completely unfamiliar. There are no horses in the Paleocene forest, no dogs, no cats, no deer, no elephants, none of the familiar large mammals of the modern world. Those don't come until later. What you have instead are the condylarths, generalized hoofed mammals that were ancestors or close ancestors of many modern groups. They looked a bit like small dogs with hooves instead of paws and teeth that could handle both plants and meat. Generalists, as all survivors of catastrophe tend to be, and the multituberculates, these are the strangest of the early Cenozoic mammals. They'd been around since the Jurassic, some of the oldest mammal lineages on Earth. By the Paleocene, they were diverse and successful. They look superficially like rodents, small, with gnawing front teeth. But they're not rodents. They're not related to rodents. They're their own thing, an entirely separate mammalian lineage that would eventually go extinct in the Eocene, replaced by the true rodents. For now, they're one of the most common mammals on the planet, scurrying through the undergrowth, eating seeds and insects and whatever they can find, living their small, quick, ancient lives. The Paleocene world was warm, not the scorching heat of the post-impact years, but warm, warmer than today. The poles were free of ice. Forests grew in what is now Alaska. Subtropical vegetation extended to 60 degrees north latitude where London is today. The average global temperature was perhaps 4 to 8 degrees Celsius warmer than today. A greenhouse world powered by the CO2 released by the impact and by continued volcanic activity. The warmth was not immediate. The impact winter came first. But once the dust settled, the greenhouse gases did their work, and the world warmed, and the forests spread, and the mammals multiplied. The speed of recovery. One of the most remarkable things about the Paleocene is how quickly life recovered. Within about 300,000 years of the impact, a blink of geological time, there were large mammals. Not the giants of the later Cenozoic, but large by the standards of the immediate post-impact world. Pantolanda, a sheep-sized mammal, herbivorous, hoofed, living in the forests of North America 63 million years ago. That's only 3 million years after the impact. 3 million years from the death of the dinosaurs to a sheep-sized mammal. Life doesn't wait. Life fills every available niche as fast as the resources allow. The isolation of continents. The Paleocene world had a geography that would seem strange to us. The continents were in different positions. North America was still broadly where it is now, but South America was completely isolated, an island continent separated from North America by the seaway that would later close to form Central America. Africa was mostly isolated, too separated from Europe by the Tethys Sea. India was an island, drifting northward toward Asia at extraordinary speed by geological standards, about 15 to 20 centimeters per year. Antarctica was positioned near the South Pole, but still connected to South America and Australia. Still warm, still vegetated. This isolation was important. It meant that different continents developed their own separate mammalian faunas. Like different experiments in the same general theme, South America developed its own remarkable suite of mammals, the meridiungulates, the litoptons, the notangulates, that have no modern equivalents and no close modern relatives. Australia developed its marsupials. North America and Europe, connected occasionally by land bridges, developed their own condylarths and early ungulates and primates. Africa developed its own lineages, including the ancestors of elephants, sea cows, and hyraxes. The world of the Paleocene was not one world. It was many worlds, each developing in its own direction, each producing animals that would astonish us if we could see them. The first primates, here is something that will make tonight feel personal. In the forests of the late Paleocene, about 60 to 65 million years ago, the first primates appeared. Not humans, nothing like humans. Small tree-dwelling mammals with forward-facing eyes that gave them better depth perception, with grasping hands, with nails instead of claws on at least some digits, with larger brains relative to body size than most other mammals. Living in the tropical and subtropical forests of North America and Europe, these were the ancestors of every primate alive today. Every lemur, every monkey, every ape, every human traces its lineage back to these small, cautious, large-eyed creatures. Living in the forest canopy of the Paleocene, 66 to 56 million years ago, you were there, very small, with very large eyes, moving carefully through the trees. The Eocene, 56 to 33.9 million years ago, the world at its warmest. 56 million years ago, something happened that changed the world, and the world has never been quite the same since. The Paleocene-Eocene thermal maximum, the Batten, one of the most dramatic climate events in the last 66 million years, not caused by an asteroid, not by a supervolcano, by carbon. In the space of roughly 20,000 years, possibly less, the amount of carbon dioxide in the atmosphere doubled or more. The source, probably a massive release of methane from frozen seafloor deposits, possibly also from volcanic activity in the North Atlantic. The effect, the planet warmed by an additional 5 to 8 degrees Celsius. On top of an already warm Paleocene, the oceans warmed, the deep ocean warmed, which almost never happens because deep ocean water changes temperature on timescales of millennia. The ocean acidified as CO2 dissolved into the water. Many deep-sea foraminifera, tiny shell-building organisms, went extinct. The surface world changed dramatically. But here is the remarkable thing about the PETM. It is associated with one of the most dramatic bursts of mammalian evolution in the history of life, not an extinction, an explosion. Suddenly, in the fossil record at the PETM boundary, new mammal groups appear. Perissodactyls, the group that includes horses, rhinos, and tapirs. Artiodactyls, the group that includes pigs, deer, cattle, camels, whales. True primates, more advanced than the Paleocene Plesiadapiforms. All of them appearing, apparently rapidly, at or just after the PTM. Why? The warmth opened new habitats. Tropical forests expanded across North America and Europe. New ecological niches appeared, and the mammals filled them with extraordinary speed. The Eocene world, the Eocene lasting from 56 to about 34 million years ago, is the warmest period of the Cenozoic. The peak warmth was in the early Eocene, around 50 million years ago. The global average temperature was perhaps 10 to 15 degrees warmer than today. There were palm trees at the Arctic Circle. Tropical forests covered what is now England and Scotland. Crocodilians, which today live only in tropical and subtropical regions, lived in the Canadian Arctic and in Ellesmere Island. Antarctica, which is now covered in ice up to 4 kilometers thick, was a forested continent, a green continent, with rivers and forests and animals living along the coast. In a world where the Antarctic meant not ice and cold, but trees and warmth, I find this almost impossible to imagine. Not because the science is unclear, it's very clear, but because the world we know is so different. The places we associate with cold and emptiness, were once warm, were once full of life. The Arctic, Antarctica, these are not permanent features of a fixed world. They are the current state of a world that is always changing, always becoming something else. The animals of the Eocene was, in many ways, the golden age of experimentation. The mammals had the world to themselves. No giant predatory dinosaurs competing for the large herbivore niche, no established mammal dynasties to compete with, just open ecological space, and hundreds of mammal lineages exploring what the world had to offer. The Eohippus, the dawn horse, better known by its proper name Hyracotherium. This is the ancestor of all modern horses. And it was nothing like a horse. It was the size of a dog, a large terrier, perhaps, with 4 toes on each front foot and 3 on each back, with low-crowned teeth suited for eating soft leaves in the tropical forest, not the tall-crowned grinding teeth of the grass-eating horses of later ages. The Eohippus didn't run on open plains. It hid in forests. It was not the noble creature we associate with horses. It was shy, small, quick to flee, living in the warm forests of Eocene North America 50 million years ago. The Uintatherium. Here is an animal that deserves to be better known, a massive herbivore from the Eocene of North America, roughly the size of a large rhinoceros, with 6 bony protrusions on its skull, 3 pairs of knobs and horns arranged across the top of the head, and in the males, a pair of saber-like upper canine teeth, not for eating meat, for competing with other Uintatherium, for display, for dominance. A bizarre, heavily armed herbivore that went extinct at the end of the Eocene and left no descendants, an evolutionary experiment that the universe tried and then abandoned. The Basilosaurus. This one might be the most extraordinary. The Eocene was the age when whales made their transition from land to sea, and Basilosaurus, despite its name, which means king lizard, was not a lizard. It was a whale, an early whale, 18 meters long, with a long serpentine body, tiny vestigial hind legs actually present, probably used in mating, a skull full of complex interlocking teeth, not the filter-feeding whales of today, but an active predator, hunting sharks, other whales, large fish. In the warm Eocene ocean, the story of how whales got into the ocean is one of my favorite stories in all of evolutionary biology, because it happened so fast, and the evidence is so clear. The ancestor of all whales was a land animal, related to the even-toed ungulates, the artiodactyls. In fact, the closest living relatives of whales are hippos. Not metaphorically, actually, genetically. Whales and hippos share a common ancestor more recently than hippos share an ancestor with other ungulates. The transition from land to sea happened in the early Eocene. Within about 10 million years, the fossil record shows the stages. Pachycetus, a wolf-sized, 4-legged animal, semi-aquatic, could walk on land but spend time in rivers. Ambulocetus, already more aquatic, its legs modified for swimming, but still able to walk. Rhodhocetus, even more aquatic, hind legs small and probably not useful for walking. Basilosaurus, fully marine, hind legs vestigial, 10 million years. From a wolf-like land mammal to an 1.8-meter ocean predator, the most dramatic transition in mammalian evolution, happening right here in the warm Eocene Sea. The primates diversify In the warm Eocene forests, the primates were having their moment. True primates, more advanced than the Paleocene forms, diversified into a remarkable array of species. Adapiforms, oomyforms, early prosimians, living in the canopy of the tropical forests that covered much of the northern hemisphere. These primates were small, most of them smaller than modern squirrels, but they had the primate features that would define the lineage: binocular vision, grasping hands, complex social behaviors, large brains relative to body size. And the Eocene primates were in North America and Europe, not in Africa and Asia as most modern primates are. North America was a primate paradise in the Eocene until it wasn't. The great cooling 34 to 23 million years ago, the Oligocene, nothing lasts. This is the geological lesson that the Cenozoic teaches more clearly than anything else. The warmth of the Eocene, the lush tropical forests, the palm trees at the Arctic Circle, the green Antarctic, all of it ended. Not quickly, not in a single catastrophe, but inexorably. Over millions of years, the world cooled. The Eocene-Oligocene transition, about 34 million years ago, was one of the most significant climate shifts of the entire Cenozoic. The global temperature dropped dramatically. Ice sheets began to form on Antarctica for the first time in tens of millions of years. Sea levels dropped. The tropical forests that had covered the northern hemisphere retreated south. The world became drier. Why did it cool? Several factors came together. The opening of the Drake Passage, the deep channel between South America and Antarctica, which allowed the circumpolar current to form around Antarctica, a current that isolated Antarctica thermally, cutting off the warm tropical water that had been flowing toward it. Antarctica began to cool. The ice began to build. Once ice forms, it reflects sunlight, the albedo effect. Reflecting more sunlight makes it colder. More ice forms, which reflects more sunlight. A feedback loop, a self-reinforcing cycle of cooling. Also, declining CO2. The concentration of carbon dioxide in the atmosphere had been declining since the Eocene maximum. As the world cooled and forests spread, more carbon was locked up in organic matter. Less CO2 meant less greenhouse warming. A cooler world. The animals of the Oligocene had to adapt or go extinct. Many did go extinct. The Eocene faunas, the condylarths, the early ungulates, many of the early primates were replaced by more modern-looking forms. The world was changing, and the animals were changing with it. The Oligocene world. The Oligocene is sometimes called the forgotten epoch. Less dramatic than the warm Eocene. Less dramatic than the ice ages that would come later. A transitional time. The world between, but remarkable in its own ways. The continents were shifting. India was colliding with Asia. Dramatically. The Himalayas were rising, not yet to their full height, that would come later, but rising. Africa was approaching Europe. The Tethys Sea, the ancient ocean that had separated Africa from Europe for tens of millions of years, was narrowing. Eventually it would be gone, and the Mediterranean would be all that remained. The grasses. Here is a development that would change the world. In the Oligocene, grasses began their expansion. Grasses had existed since the late Cretaceous, but they had been minor components of the vegetation. In the cooler, drier Oligocene, they began to spread. Grasslands began to appear in the places where forests had retreated, in the interiors of continents, where The climate was now too dry for trees. The grasses filled that space, and the grasses would change everything because the grasses would drive the evolution of the animals that ate them, and the animals that ate the grass would drive the evolution of the animals that ate them. A cascade of evolutionary consequences, starting with a change in the vegetation, starting with the spread of grass, the giant rhinoceros, the Oligocene of Asia produced something extraordinary. The Paracerathers, the largest land mammals that have ever existed, larger than any dinosaur that walked on land. The most famous Paraceratherium, formerly known as Indricotherium or Baluchitherium, a hornless rhinoceros relative, about 8 meters tall at the shoulder, about 9 meters long, weighing an estimated 15 to 20 tons, a giraffe-like neck, browsing from the tops of trees in the warm forests of Oligocene Asia. When I first read about Paraceratherium, I had to look at the scale diagrams for a long time because the numbers don't prepare you for the images. 8 meters tall at the shoulder, that's a 2-story building. An animal the height of a 2-story building walking through the forests of Pakistan and Kazakhstan 30 million years ago. A real animal made of blood and bone with a heartbeat that browsed from the tops of trees that no modern animal can reach because no modern animal is that tall. Paraceratherium was the largest land mammal that has ever lived, and almost nobody knows it existed. The Miocene, 23 to 5.3 million years ago, the Golden Age, the Miocene, the longest epoch of the Neogene, lasting 18 million years, from 23 million years ago to 5.3 million years ago. In many ways, the most important epoch for understanding the modern world, because the Miocene built the foundation of everything that came after. The climate of the Miocene was broadly warmer than today. The early Miocene saw a warming period, the Miocene climate optimum around 15 to 17 million years ago. Global temperatures perhaps 3 to 4 degrees warmer than today. Ice on Antarctica, but less of it than today. No permanent ice on the Arctic. Then cooling, again, around 14 million years ago, a second major cooling event. The expansion of Antarctic ice, the further retreat of tropical forests, the further expansion of grasslands, the grasslands. The Miocene was the age when grasslands became a dominant biome, spreading across the interiors of the continents. North America, Eurasia, Africa, South America, vast open landscapes with no trees, or very few trees, covered in grass. And the animals that lived on grass and the predators that hunted those animals, for the mammals that lived in or near these new grasslands, the evolutionary pressure was intense. The grasslands rewarded specific adaptations, being fast enough to see predators coming and run from them across open country, having teeth tough enough to grind the silica-rich grass, being able to travel long distances between patches of water, being social, large herds meant more eyes, more warning of predators. The animals that could do these things thrived. The animals that couldn't were replaced. The horses evolve. Remember the Eohippus, the dog-sized, four-toed forest horse of the Eocene? By the Miocene, horses had been evolving for 30 million years. And the evolution was not random. It tracked the grasslands. As the grasslands spread, horses evolved. Teeth grew higher crowned, better for grinding tough grass. Legs grew longer, better for running on open plains. Toes were reduced from 4 to 3 in many Miocene forms, and eventually, in modern horses, to 1, the single hoof. the most efficient form for running on hard ground. Brains grew larger. The complexity of social life in open habitats required more cognitive processing. Body size increased. Larger animals can travel farther between food and water sources. The horse lineage, over 55 million years, is one of the most beautiful examples of evolution we have. Not a straight line, horses diversified into many different forms, many of which went extinct but a general direction, toward the animal we know today, shaped by the grasslands. The apes. The Miocene was the age of apes, not human apes, not even close, but the age when the ape family hominoids diversified into an extraordinary variety of forms. In the Miocene fossil record, we find dozens of ape species in Africa, in Asia, in Europe. Apes in the Miocene were far more diverse than apes today. They filled many ecological roles: large frugivores, small insectivores, terrestrial foragers, arboreal specialists. Some of the Miocene apes were enormous. Gigantopithecus, which we'll come to in more detail, first appeared in Asia in the Miocene. Some were tiny. Some looked more like monkeys. Some looked more like modern apes. And among all of them, somewhere, were the ancestors of the lineages that would eventually produce chimpanzees, gorillas, and us. The Miocene was the age of possibility, when the great ape family was at its most diverse, when the future was not yet determined, when there were dozens of different answers to the question of what a large-brained social arboreal primate could be. Before most of those answers went extinct, and the world was left with only a few, including ours, the whales diversify. In the warm Miocene oceans, the whales continued their extraordinary diversification. Mysticets, the baleen whales, had appeared in the Oligocene, and in the Miocene they diversified explosively. As the cooling oceans became more productive, cold water holds more oxygen, which supports more phytoplankton, which supports more krill. The baleen whales, filter feeding on krill, had an enormous food source, and they grew. The giant baleen whales of the modern ocean, the blue whale, the fin whale, the humpback, are products of this Miocene expansion, shaped by the productivity of cold water oceans, by the extraordinary abundance of tiny crustaceans that the cooling world produced. The megalodon. Speaking of the oceans, the Miocene was also the age of megalodon, the largest shark that has ever lived, estimated at 15 to 20 meters in length, weighing perhaps 50 to 100 tons, with teeth up to 18 centimeters long, serrated for cutting through the blubber and bone of large whales. Megalodon hunted the giant baleen whales of the Miocene ocean. We know this from fossils. Whale bones with megalodon bite marks, the puncture patterns consistent with a shark that attacked the tail, immobilizing the whale before moving in to feed. A predator, of the largest prey in the history of the oceans. And megalodon was not rare. Its teeth are found in marine sediments on every continent, scattered across every ocean basin. It was the apex predator of the Miocene ocean for millions of years, a presence in the ocean. That shaped the behavior of every large marine animal. That drove the evolution of whales towards size, towards speed, toward behaviors that avoided the great shark. Gone now, about 3.6 million years ago, when the cooling oceans changed the distribution of the large whale populations that megalodon depended on. When the warm Miocene seas became the colder Pliocene seas, and the prey moved to colder waters. where perhaps the cold itself, or the different productivity, or the changed whale behavior in the cold made the great shark's hunting strategy fail, and Megalodon went extinct, not with drama, but with the slow, quiet fading of a lineage whose world had changed and who could not change with it. The giants, the creatures nobody told you about. Let me stop here and take you on a tour of the animals of the Cenozoic that almost nobody knows existed, the ones that should be famous, the ones that deserve to be in every museum. That should be on the poster. That should be the thing people picture when someone says prehistoric mammal. Andrewsarchus. Start here, because this one is genuinely terrifying. Andrewsarchus mongoliensis, known from a single skull found in Mongolia in 1923. The skull is 83 centimeters long, with teeth like railroad spikes. The largest skull of any known land carnivore in the history of mammals. Based on scaling from the skull, the complete animal may have been 4 meters long, weighing perhaps half a ton. A predator of the Eocene, living 45 million years ago. And here is the strange part. Andrewsarchus is related to the Mesonychids, a group of carnivorous ungulates, animals with hooves. Andrewsarchus was a carnivore with hooves. The closest living relative of Andrewsarchus, according to some analyses, may be the whales, a giant hoofed predator, related to whales, stalking the Eocene landscape with a skull the size of your coffee table, Entelodon, sometimes called the hell pig or the Terminator pig. But it's not actually a pig. It's an entelodont, a relative of hippos and pigs, but a separate lineage. The largest, Daeodon, stood about 2 meters at the shoulder, with a skull a meter long, teeth designed for crushing bone, bony flanges on the skull that may have been display structures, or for protection during fights. Evidence of healed wounds from other entelodonts suggests that they fought each other. Viciously, bite marks on skulls, evidence of combat that left scars. The entelodonts were, by the evidence of their fossils, some of the most aggressive animals of the Oligocene and Miocene. Omnivores, scavengers, possibly predators, that went extinct in the early Miocene. About 19 million years ago, Gigantopithecus, the real giant ape, the one that people keep trying to turn into Bigfoot, but which was, in reality, something both more mundane and more extraordinary. Gigantopithecus blacki lived in the forests of southern China from about 2 million years ago to perhaps 100,000 years ago, or possibly later. It was enormous, the largest primate that has ever lived, estimated from its giant jaw fragments and isolated teeth at perhaps 2 to 3 meters tall when standing, weighing perhaps 200 to 300 kilograms. A fully upright Gigantopithecus would have looked like a gorilla but twice the size, but it probably didn't stand fully upright. Like gorillas, it likely walked on its knuckles. What did it eat? The teeth and jaw suggest bamboo, primarily, like a giant panda, a massive bamboo-eating ape living in the forests of Ice Age China, possibly alongside early Homo sapiens before it went extinct. We don't know exactly why. Climate change, habitat loss, competition, perhaps disease. The giant ape, that was real, gone so recently that our ancestors may have seen it. Smilodon, the saber-toothed cat, everyone has heard of it. Fewer people know how extraordinary it actually was. 3 species, the largest Smilodon populator from South America, weighing perhaps 400 kilograms, more heavily built than a modern lion, with saber teeth up to 28 centimeters long, fragile, serrated, designed not for biting through bone they would break, but for cutting through soft tissue. The throat of prey, in a killing bite that was less like a lion's crushing bite and more like a pair of scissors. The prey was held still by the strong forelimbs with their retractile claws while the sabers delivered a precise, lethal wound. What prey? In North America, horses, camels, bison, ground sloths. In South America, giant ground sloths, glyptodons, horses, prey as large as or larger than Smilodon itself. The musculature suggests extreme upper body strength. The limbs were shorter than a modern lion's, not a long-distance runner, an ambush predator, waiting in cover for prey to come close. Then the explosive rush, the powerful forelimbs bringing prey down, the sabers delivering the kill, the giant ground sloths. If Smilodon was the predator, these were the prey, or some of the prey, Megatherium americanum, the giant ground sloth of South America, 9 meters long, 4 tonnes, larger than an elephant, with curved claws on its front limbs up to 50 centimeters long, not for killing, for pulling down tree branches, for digging up roots, a herbivore, an enormous, slow-moving herbivore that could rear up on its hind legs using its thick tail as a prop and reach 6 meters into the trees. Living in South America from the Miocene to the late Pleistocene, going extinct about 10,000 years ago, overlapping with the first humans in the Americas. Who may have been responsible for its extinction? The glyptodonts, relatives of armadillos. But imagine an armadillo the size of a small car, a domed, bony shell of fused hexagonal plates covering the entire body, weighing up to 2 tons, with a tail that in some species ended in a bony club or spikes used against predators and against other glyptodons in competition, a living fortress that trundled through the grasslands of South America and eventually North America when the two continents connected for millions of years before going extinct in the late Pleistocene. Another casualty of the combination of climate change and human hunting, the Pliocene, 5.3 to 2.6 million years ago, the last warm world, the Pliocene, a short epoch, only about 2.7 million years, but one of the most significant in the entire Cenozoic. For one specific reason, our ancestors were walking upright in the forests and savannas of East Africa. The hominins, our lineage, had been diversifying for millions of years. The split between the lineage leading to chimpanzees and the lineage leading to humans happened somewhere between 7 and 10 million years ago in the Miocene. Exact date uncertain. But by the Pliocene, there were several species of bipedal hominins walking through the African landscape. Australopithecus, Paranthropus, early Homo, not modern humans, not yet, but upright, two-legged, with brains somewhat larger than chimps, hands adapted for precision grip as well as power, making tools, simple stone tools, but tools nonetheless, living on the African savanna in a world that was cooling, drying, changing. The most famous is Lucy, Australopithecus afarensis, 3.2 million years old, found in Ethiopia in 1974. A partial skeleton of a female just over a meter tall, with a brain about the size of a chimpanzee's, but walking upright, confidently from the structure of her knee, her pelvis, her foot. When I think about Lucy, I think about what she could not have known, that her lineage would go on, that 3.2 million years after she walked through the forests and grasslands of Ethiopia, her descendants would be lying in rooms, in buildings, on a world covered in electric light, listening to a voice describing her. She couldn't have known. She was just a small, upright ape, living her life in a world that was already beginning to change into something she couldn't imagine. The Pliocene climate, warmer than today. The early Pliocene, 5 to 3 million years ago, had global temperatures perhaps 2 to 3 degrees warmer than pre-industrial levels. The Arctic was ice-free in summer. Sea levels were higher, perhaps 15 to 25 meters higher than today. Coastal landscapes looked very different. The Mediterranean was a different sea. The African landscape was different, more forests, more lakes. The conditions in which our ancestors evolved were warmer, wetter, more forested in places than the Africa we see today. Then, around 3 million years ago, the northern hemisphere began to glaciate. For the first time in the Cenozoic, Arctic ice formed, Greenland glaciated. The ice ages were beginning, the long oscillation between cold and cold and cold, with brief warm periods in between that would characterize the Pleistocene. The epoch that came next, the epoch of mammoths and mastodons and Neanderthals and us, the great American interchange, when two worlds collided 3 million years ago. Something happened in the geography of the Americas that would have profound consequences for the animals of two continents. For 60 million years, North and South America had been separated. A deep seaway, the Central American Seaway, ran between them. North America had its own fauna. South America had its own two completely different evolutionary experiments running in parallel for 60 million years. Then, about 3 million years ago, the Isthmus of Panama formed. The two continents connected, the seaway closed. And for the first time in 60 million years, the animals of North and South America could meet, the Great American Biotic Interchange, one of the most dramatic natural experiments in evolutionary history. What happened when animals from two long isolated faunas were suddenly free to move between their worlds. The North American invaders went south. Horses, tapirs, mastodons, deer, llamas, pumas, jaguars, wolves, bears moved into South America. Some thrived, some didn't. The horses flourished in South America and would later go extinct there too, with the human arrival. The cats, the ancestors of pumas and jaguars, thrived and diversified. The canids, wolves, and foxes expanded. The South American animals went north. Glyptodon, giant ground sloths, capybaras, armadillos, opossums moved into North America, some of them spectacularly successful. Giant ground sloths reached as far north as Alaska. Glyptodons reached as far north as Texas and Florida. The opossums, little, simple, ancient marsupials, spread across the entire continent and are still here, the only marsupial native to North America. The overall result of the interchange was not equal. The North American invaders were generally more successful in South America than the South American animals were in North America. The North American carnivores, the cats, the wolves, were more efficient predators. than the South American carnivores they encountered. The terror birds, the forahacids, the apex predators of South America for 60 million years, were outcompeted by the invading mammalian carnivores and went extinct within a few million years. The balance of the South American ecosystem was disrupted profoundly by the closure of the Panama Seaway, by the meeting of two worlds that had been apart for 60 million years. The Pleistocene, 2.6 million to 11,700 years ago, the Ice Age world, the Pleistocene, the Ice Age, or more precisely, the series of ice ages that dominated the last 2.6 million years of Earth's history. The Pleistocene is defined by the ice, massive ice sheets that advanced across North America and Europe and Asia. During the glacial periods, ice 2 to 3 kilometers thick, covering what is now Canada, covering Scandinavia, covering much of Russia, sea levels dropping as water was locked up in the ice. The world constricted, but the ice was not constant. The Pleistocene oscillated between glacial periods, cold, with massive ice sheets, and interglacial periods, warm, more like today, roughly every 100,000 years, with smaller cycles of 41,000 and 23,000 years overlaid on top, driven by variations in the Earth's orbit and axial tilt, the Milankovitch cycles, the Earth's orbital mechanics, determining the climate on timescales of tens of thousands of years. The Pleistocene was the age of megafauna, of giant mammals living across every continent, of a world full of enormous creatures that would stagger us if we saw them. The mammoth steppe, the vast grassland that ran from Britain to China during the glacial periods, when much of northern Eurasia was not covered by ice. The ice was primarily to the north and west, but was cold, dry, open. A grassland, more like the modern Mongolian steppe than anything we see in Western Europe today, crossed by vast herds of animals. Woolly mammoths, the icon, the symbol of the Ice Age. Mammutus primigenus, not as large as the earlier Columbian mammoth of North America, but large, perhaps 3 to 3.5 meters at the shoulder, up to 6 ton, with tusks up to 4 meters long, curved spirally, used for sweeping snow aside to find vegetation beneath, and for display, and for combat, covered in a dense coat of long, dark hair, with a layer of fat beneath for insulation, roaming the mammoth steppe in herds. From Western Europe to North America, we know more about woolly mammoths than almost any other extinct animal because of permafrost. Frozen remains, complete or near complete bodies found in the permafrost of Siberia, not fossils, bones replaced by minerals, but actual bodies with flesh and hair and stomach contents intact. The stomach contents of mammoths found in permafrost have been analyzed. We know what they ate: grasses, sedges, mosses, shrubs. We know their last meals. One mammoth found in Siberia had buttercups in its mouth, still green, preserved by the freezing, the last thing it ate before it died and froze, and was preserved for 30,000 years. The woolly rhinoceros, alongside the mammoths. Coelodonta antiquitatis, the woolly rhinoceros, about 3.5 meters long, with 2 horns, the front horn up to 1.5 meters long. The horn was made of keratin, the same material as human fingernails. And keratin doesn't fossilize well, but it can be preserved in permafrost. A woolly rhinoceros horn was found in an ancient salt mine in Ukraine, still intact, after 30,000 years. Cave paintings in France and Spain show the woolly rhinoceros. The Ice Age hunters knew this animal, painted it, hunted it, perhaps revered it. The cave bears, Ursus spelaeus, the cave bear, living in Europe from about 250,000 to about 24,000 years ago, larger than a modern brown bear, but a herbivore, primarily. The skull is massive, the teeth adapted for crushing plant matter. The cave bear is known from thousands of fossils because of where it died. In caves, caves that were used as hibernation sites, and where old, weak, injured bears went to die. Over tens of thousands of years, the bones accumulated in caves across Europe, bones of cave bears, sometimes mixed with the bones of cave lions and cave hyenas and Neanderthals, who also used caves for shelter. The caves of Ice Age Europe were contested spaces, shared reluctantly between species that had different claims on the same shelter, the same fire, the same darkness. The Irish elk, Megaloceros giganteus, the largest deer that has ever lived, standing about 2 meters at the shoulder, with antlers spanning up to 3.7 meters, the largest antlers of any known animal. In proportion to body size, these antlers were not for fighting. They were too big for fighting in forest environments. They were for display, for impressing females, for intimidating rival males. A distance, a visual spectacle, a flog, saying, "Look at me, look at what I can grow." The Irish elk is famous partly because of a historical misunderstanding. When the first specimens were found in Irish peat bogs in the 17th and 18th centuries, people called them giant deer of Ireland. But they weren't just from Ireland, and they weren't just deer. They lived across Eurasia, from Ireland to China, from Siberia to North Africa, for 400,000 years before going extinct. About 7,700 years ago, one of the last to go, the humans arrive, and then there were us. Through all of this, through the warming Pliocene, and the cycling ice ages of the Pleistocene, our lineage was evolving. By 2 million years ago, Homo habilis, the handyman, the first member of the genus Homo, using stone tools systematically in East Africa. By 1.8 million years ago, Homo erectus, the first human species to leave Africa, spreading across Eurasia, reaching Georgia, India, Indonesia, China, living for nearly 2 million years, the longest-lived human species we know of, controlling fire, making more sophisticated tools, with a brain about 75% the size of ours. By 300,000 years ago, Homo sapiens was in Africa with a full modern anatomy and full modern cognitive capacity, and by 45,000 to 50,000 years ago, Homo sapiens in Europe, meeting the Neanderthals, who had lived there for 200,000 years, the Neanderthals. I want to spend a moment here because they are easy to dismiss as primitive, as our inferior precursors, who were replaced by us. But the Neanderthals were remarkable. They buried their dead. They made jewelry. They made paint red ochre and black manganese dioxide. They made tools that were sophisticated for their time. They cared for their sick and injured. Shanidar I, the Neanderthal we have discussed in other episodes, survived multiple severe injuries, only because others cared for him. They were not us. Their anatomy was different, heavier, more robust, larger brow ridges, no chin, a different skull shape, a different brain shape. Though similar in volume, they were a different kind of human, not a lesser one, a different answer to the question of what a large-brained, social, tool-using primate could be. We interbred with them. The DNA of modern non-African humans is 1 to 4% Neanderthal. Some of that DNA has functional effects on our immune system, on our metabolism, on our pain response, on our sleep patterns. Some research suggests that Neanderthal DNA affects circadian rhythms. The Neanderthals are not entirely gone. They live in us, in our cells, in the code that runs the body you're lying in right now. The last Neanderthals went extinct about 40,000 years ago, possibly 28,000 years ago in some isolated populations. Gibraltar may have been one of the last refugia, the Rock of Gibraltar, where the last Neanderthals may have looked out over the Mediterranean. In the late Pleistocene, before their line ended, the great dying again, the Pleistocene megafauna extinction, something happened about 50,000 to 10,000 years ago that we have not yet fully reckoned with. The largest extinction of large animals since the end of the dinosaurs. In the Pleistocene, Earth was full of giant mammals. In Africa, giant buffalo, giant wildebeest, giant giraffes. In Eurasia, woolly mammoths, woolly rhinos, cave bears, cave lions, cave hyenas, Irish elk. In Australia, diprotodons, giant kangaroos, marsupial lions, giant wombats, giant birds. In North America, mammoths, mastodons, horses, camels, ground sloths, saber-toothed cats, dire wolves, short-faced bears. In South America, glyptodons, giant ground sloths, horses, giant capybaras, terror birds. Within a few thousand years of humans arriving on each continent, most of these animals were gone. The pattern repeats. Australia. Humans arrive about 65,000 years ago. By 40,000 years ago, most of the megafauna are extinct. North America. Humans arrive about 15,000 to 20,000 years ago. By 10,000 years ago, 33 of 45 genera of large mammals are extinct. South America, similar timing, similar pattern. Africa and Eurasia. The extinctions were more gradual because the megafauna had more time to evolve wariness of human hunters, but still significant. Was it us? The climate was also changing. The ice ages were ending. The habitats were shifting. Climate change and human hunting happened at the same time. Disentangling them is difficult, but the pattern is damning. Every continent shows large animals thriving for millions of years, and then going extinct within a few thousand years of human arrival, not during previous climate changes of similar magnitude, not during previous ice age cycles, but when humans arrived. I find this one of the most sobering facts about our species. Not that we are evil, not that the early hunters were malicious. They were doing what hunters do, following prey, without any way of knowing that they were hunting an animal toward extinction, without any concept of extinction, without the ability to see that the mammoths were getting fewer and fewer and fewer until there were none. The last woolly mammoths died on Wrangel Island, a small island in the Arctic Ocean, north of Siberia, about 4,000 years ago. The pyramids were already standing when the last mammoths died. The great Egyptian civilization was already centuries old. somewhere on a small Arctic island, a small, isolated population of woolly mammoths, the last of their kind, was eating grass in the cold, not knowing they were the last, not knowing that no one would come after them, that the line that had existed for a million years would end with them on this island in the cold, the Holocene, the world we inherited 11,700 years ago. The last ice age ended. The Younger Dryas, a sudden cold snap that had interrupted the warming, finally ended. The temperatures rose. The ice sheets retreated. The sea levels rose. The world began to look like the world we know. The Holocene, our epoch, the current one, the warm period that we live in. The Holocene began with forests growing across Europe and North America, where ice had been tundra first, then birch forests, then the mixed temperate forests we know. In North Africa, the Sahara was green, the African humid period. Rivers, lakes, savanna, people living there, herding cattle, painting on the rocks, hippos in what is now the middle of the Sahara. The world was different, more alive, more varied, more lush, in many ways, than the world of today. And in this new world, the remaining human populations did something new, something that had never been done before. In the entire 300,000-year history of our species, they farmed the agricultural revolution about 10,000 to 12,000 years ago in the Fertile Crescent, and then independently in China, in New Guinea, in Mesoamerica, in South America, in West Africa. People began to deliberately cultivate plants and keep animals and stay in one place and build. This is where civilization begins. This is the point from which everything we call history unfolds. The cities, the writing, the empires, the technology, all of it growing from this moment when our ancestors decided to stop following the food and make the food come to them. From Australopithecus to agriculture, in 3 million years, from the first stone tools to the first cities in 3 million years, of the 66 million years since the dinosaurs in the context of the Cenozoic. That is nothing, a fraction of the time that the mammals had been building toward this. The world now, what the Cenozoic built, stands still for a moment. In whatever room you're in, and look at the world around you. Everything alive today is the product of 66 million years of the Cenozoic. The cat on your bed is the descendant of Paleocene carnivorous mammals that evolved through 66 million years into the domestic cat, which still hunts in the same way its ancestors did in the forests of 50 million years ago. The flowers in any window box are the refined descendants of flowering plants that exploded into diversity in the Eocene, in the warm world that preceded our cooling one. The dog is a domesticated wolf, and the wolf is the product of Miocene Canidevolution on the grasslands of North America. The grass outside, the lawn, the field, the meadow is the product of the Oligocene and Miocene expansion of grasslands that changed the entire trajectory of mammalian evolution. The mountains, the Himalayas, the Alps, the Rockies, the Andes were built during the Cenozoic, rising as the tectonic plates moved into their current positions. The mountains that define our world are 30 to 50 million years old. young by geological standards, products of the Cenozoic, the ocean currents that drive the climate of Europe, of the Americas, of the entire world were established when the continents reached their current positions, when the Drake Passage opened, when the Panama Isthmus closed, when the Indian Ocean circulation pattern was set by the northward movement of India and Africa. The world's climate is a product of Cenozoic geography, and every feature of your body, every capacity of your mind is the product of 66 million years of mammalian evolution. In the Cenozoic, your forward-facing eyes, inherited from your primate ancestors, who needed depth perception to navigate the forest canopy, your opposable thumbs, developed for grasping branches, long before they held tools. Your large brain, built up over millions of years of social primate life under the evolutionary pressure of increasingly complex social environments, your capacity for language, your capacity for culture, your capacity for art and music and mathematics and love, all of it products of a 6 million year process that started in the darkness. After an asteroid fell, the animals we lost, a lament for what is gone. Let me take a moment to mourn for the things that are gone. The mammoth, the last one died 4,000 years ago on the Wrangel Island in the Arctic. The creature that the Ice Age hunters painted on cave walls, the creature that had survived multiple Ice Age cycles, that had lived across the entire northern hemisphere, gone now, its bones in permafrost, its DNA preserved. Scientists are trying to bring it back, using CRISPR technology to edit elephant DNA toward a cold-adapted mammoth-like form. Whether they should, whether they will, is one of the most profound ethical questions of our time. The saber-toothed cat, Smilodon, gone about 10,000 years ago, the most specialized cat predator that ever lived, the most perfectly adapted for a specific kind of hunting in a specific world that no longer exists, because the prey is gone, because the world changed. The terror bird, Titanis wallere, the last North American terror bird, a 2-meter tall, flightless predator, gone about 2 million years ago, when the carnivorous mammals from South America were a more successful strategy in the changed world of the Great American Interchange. Every extinction is a permanent subtraction from the diversity of life, a lineage tested and refined over millions of years. Gone, irrevocably, the specific combination of characteristics that defined that animal will never exist again. Not exactly. Evolution doesn't repeat itself. The specific path that produced Smilodon or Paraceratherium or the Irish elk, those paths are closed. Those animals are truly forever gone. There is a word for this in the vocabulary of conservation biology: defaunation, the loss of fauna, the emptying of the world of its animals. We are living through a defaunation event. Now, the 6th mass extinction, driven not by an asteroid, but by habitat destruction, by climate change, by hunting, by pollution. Those, the same species that inherited the world after the last great extinction is now driving another one, the Cenozoic era, built extraordinary diversity over 66 million years, species by species, adaptation by adaptation. The mammals diversified into tens of thousands of species, filling every possible niche on every possible continent, in every possible climate, from the Arctic to the tropics, from the deepest ocean to the highest mountain, and we are losing it faster than it has ever been lost. Since the asteroid, since the day the sky fell, the long view, what 66 million years teaches us, I want to end with perspective, not to diminish the urgency of what is happening now, but to situate it in the longest possible context. The Earth has survived worse, much worse, 5 mass extinctions before the current one. Each time, life came back, different, changed, but abundant, diverse, full of new forms, exploring new possibilities that the extinction had opened up. The Cenozoic itself is the story of recovery from the worst mass extinction event in 100 million years, from 75% of species gone, from a world in darkness and cold, to a world with 10,000 species of birds and 5,500 species of mammals and millions of species of insects and trees on every continent except Antarctica, and whales in every ocean, and bees in every meadow, and fish in every stream. Life is tenacious in a way that is almost difficult to believe until you know the history, until you understand that this world, this specific, extraordinary, improbable world, with all its specific, extraordinary, improbable creatures, was built from ashes, from darkness, from a handful of survivors, in a broken world, over 66 million years, one generation at a time. And the question that the Cenozoic raises more than any other is not about the past. It is about the future. What are we building? What world are we leaving? What will the 67 million year mark look like? What will be alive then? What stories will that world tell? About us? About what we chose? When we had the choice, the mammals chose, not consciously, not with intention, but they chose. Through their evolution, their behavior, their adaptations, they chose to diversify, to specialize, to fill every niche, to explore every possibility that the post-extinction world offered, and the result was the Cenozoic, 66 million years of extraordinary life. We are choosing now, with consciousness, with intention, with the full weight of 66 million years of evolutionary inheritance behind us. We are choosing what the next chapter looks like. Is not written yet. It is being written now by every decision, every choice, every action, and every inaction of the species that inherited the Cenozoic and is now determining what comes after, the choosing, what it means to be the first conscious agent of geological change for 66 million years. Change came from outside or from below. Asteroids, volcanic eruptions, orbital mechanics, the slow drift of continents, the rising and falling of carbon dioxide over millions of years of geological process, none of it chosen, none of it intended, none of it directed by anything with awareness, just physics and chemistry and blind patient accumulation of cause and effect over deep time. And then, as the first species in the history of this planet that can look at what is happening, understand why it is happening, project what will happen next, and choose differently. This is not a small thing. This is perhaps the most significant development in the history of life on Earth since the origin of photosynthesis, which transformed the atmosphere and made complex life possible. The origin of conscious agency at geological scale is at least as significant as the origin of photosynthesis, though we have not yet decided whether it will be as beneficial. The cyanobacteria that invented photosynthesis did not choose to oxygenate the atmosphere. They just did what cyanobacteria do, and the world changed. We are doing what we do, and the world is changing. The difference is we know it. We can see it. We have the data. We have the models. We have the projections. We know. And so the question is not whether we understand, but whether understanding is enough, whether knowing is sufficient to change what we do. The Cenozoic produced in 66 million years an animal capable of that question. Whether that animal is capable of the answer is what the next chapter is about. The sixth extinction, what is happening right now. Let me be honest with you about what the science says, not to frighten you, not to overwhelm you, but because this story demands honesty. We are in the middle of a mass extinction event, the sixth in the history of complex animal life. The previous five were caused by asteroid impact, by supervolcanic eruption, by glaciation, by the radical transformation of the atmosphere, by forces so large that no living thing could have prevented them. This one is caused by us, by what we eat and what we build and where we build it and what we burn and how we use the water and the soil and the forests. The numbers are stark. Species are going extinct at a rate estimated at 100 to 1,000 times the background rate, the rate at which extinctions occurred before humans, before agriculture, before industry. The background rate was perhaps one species per million species per year. The current rate is estimated at 100 to 1,000 species per million species per year or higher. We are losing species faster than we are discovering them. Some species go extinct before they are even named, before any human being has looked at them carefully enough to describe them, to give them a name, to know what they were. In the last 500 years, we have documented the extinction of more than 900 species. Those are just the ones we know about, the documented ones, the ones someone was paying attention to. The actual number is likely much higher because most species on Earth are not being watched, are not being counted, are simply present or absent without anyone noticing the difference. The loss of individuals is even more dramatic than the loss of species. A 2018 study found that since the emergence of human civilization, about 83% of wild mammals have been lost. Not species, individuals. 83% of the wild mammals that existed before agriculture. Aragon, the living world, is a shadow of what it was 10,000 years ago. And 10,000 years ago, It was already a shadow of what it had been before the Pleistocene megafauna extinctions. We inherited a depleted world, and we have continued to deplete it. This is the honest account of the species that inherited the Cenozoic, the resilience, what life does in the face of loss. And yet, I want to tell you something else, something that the 66 million years of the Cenozoic teaches. With equal force, life is not fragile, not ultimately, not in the long run. Life is the most resilient thing we know of in the universe. After the Cretaceous impact, after 75% of species went extinct, after the darkness and the cold and the acid oceans, after all of that, life came back within 300,000 years. There were large mammals within 1 million years. There were diverse ecosystems within 10 million years. The world was as full as it had been before, just different animals, different plants, different relationships, but full, alive, extraordinary. This is the lesson of the Cenozoic. Not that nothing matters, not that extinction is fine. Each extinction is a genuine loss, an irreplaceable subtraction from the diversity of life, but that life itself, the project of life, the ongoing experiment of what living things can be, is not easily stopped. It can be set back enormously for millions of years. It can be redirected, changed, transformed, but it has not stopped, not once. In 4 billion years of Earth's history, whatever happens next, whatever the sixth extinction produces, however deep the losses, life will continue in some form, in forms we cannot predict, in forms that will seem as strange and extraordinary to whatever minds exist millions of years from now, as the mammoth and the terror bird and the megalodon seem to us the future Cenozoic, what comes after us. Let us travel forward, not backward, forward into the speculative future, into what the next millions of years might hold. Not prophecy, not certainty, but extrapolation from what we know about how the earth works and what it does when given time. The continents are still moving at approximately the speed your fingernails grow, too slow to see, but over millions of years, enormous, in 50 million years, Africa will have fully collided with Europe. The Mediterranean Sea will be gone, replaced by a mountain range as tall as the Himalayas, running across what is now the Mediterranean basin, a new Alps, massive, snow-capped, running from Spain to Iran. Australia will have moved north, far enough to collide with Southeast Asia, creating a new volcanic archipelago, a new Indonesia, but larger, spanning from Australia to the Asian mainland. The Atlantic Ocean will have continued to widen, North America moving further from Europe, the Pacific Ocean narrowing, as it has been narrowing since the Jurassic, in 250 million years. Some models predict all the continents will have assembled again into a new supercontinent, sometimes called Amasya or Pangaea Ultima, a new Pangaea, as all the land assembles in one place on one side of the planet, and the single ocean covers the other half. This has happened before, multiple times. In the history of the Earth, it will happen again. And every time it happens, the climate changes, the ocean circulation changes, the distribution of life changes, the evolutionary pressures change, and something new arises. In the changed world, the future Earth is not a dead planet. It is a planet in the middle of its story, 4.6 billion years old, approximately halfway through its expected lifespan, before the expanding sun makes it uninhabitable. In another 4 to 5 billion years, the story is only half told. The deep future animals, what evolution might produce, speculative necessarily, but grounded in what we know about how evolution works and what it tends to do with available ecological space. If the current extinction event continues, if the large mammals of the modern world are mostly lost, the ecological niches they occupied will not remain empty. They never do. Evolution fills empty niches. Given time, the question is, with what? The most likely candidates are the groups that are currently thriving, the groups that are small, generalist, adaptable, resistant to the changes humans are producing. Rodents, the most successful order of mammals, by species count, by individual count, by ecological range. Rodents live everywhere, eat almost anything, reproduce rapidly, adapt quickly. If the large mammals go, the rodents will diversify into the niches they leave. Given 10 million years, you might have rodents the size of horses, rodents filling the grazing niche of the cattle and horses and deer that are now declining. You might have large predatory rodents filling the niche of the cats and wolves. This has happened before in the isolated South American continent, where rodents diversified into many large forms that filled niches otherwise occupied by ungulates. The capybara, already the size of a large dog, is a glimpse of what rodents can become given the opportunity and time. Corvids, the crows, the ravens, the jays, the most cognitively sophisticated birds alive, already demonstrating problem-solving abilities, social learning, tool use, long-term memory, face recognition, future planning. These are the birds that have already adapted most successfully to the human-dominated world. They thrive in cities. They exploit agricultural landscapes. They have learned to use traffic to crack open nuts, dropping them in front of cars, and waiting for the light before retrieving the cracked nut. They learn, they teach each other, they accumulate cultural knowledge over generations. The corvids are perhaps the most promising lineage for complex behavioral evolution in the human-impacted world given 10 million years, given the cognitive capacity already present and the evolutionary pressure of complex environments. What might corvid intelligence become? We cannot know, but the trajectory is visible already in the birds that watch us from the telephone wire with those assessing eyes, the sun's long life, the star that makes it all possible. The sun is 4.6 billion years old, a middle-aged star in the middle of its main sequence, fusing hydrogen to helium. In its core, as it has been doing since before the Earth existed, the sun will continue in roughly its current form for another 4 to 5 billion years, giving the Earth's biosphere 4 to 5 billion years of continued solar energy, more than enough time for life to recover from whatever damage is done in the current extinction event, more than enough time for new species to evolve, new ecosystems to develop, new forms of complexity that we cannot imagine to arise. The sun is not the threat, not yet, not for billions of years. But it is changing. Slowly, the sun is about 30% brighter now than it was when life first arose. 4 billion years ago, and it continues to brighten about 1% every 100 million years. In about 1 billion years, the sun would be bright enough that the Earth's surface temperature would begin to exceed the tolerance of complex multicellular life in the tropics first, then spreading toward the poles. Over hundreds of millions of years, the oceans will begin to evaporate. The water vapor, a powerful greenhouse gas, will warm the planet further in a positive feedback, a runaway greenhouse effect that will ultimately strip the Earth of its oceans and leave a dry, hot, Venus like world. In about 1 to 2 billion years, if nothing intervenes, 1 to 2 billion years from now, that is a long time, long enough for the rodent-descended grazers and the corvid-descended intelligences and whatever other extraordinary forms evolution will produce in the aftermath of the current extinction to have the time, their age, their chapter in the Earth's long story, the lessons in the layers, what the rock remembers. The rocks remember everything, every extinction, every recovery, every warm period, every ice age, every time the carbon dioxide rose, and every time it fell. The rocks remember in their chemistry, in their isotopic ratios, in the fossils locked in their layers, in the patterns of their deposition. We can read the history of the planet from the rocks, from the thin layers of clay and chalk and limestone and shale that accumulated over billions of years, one grain of sediment at a time, the KPG boundary, the thin layer of iridium-rich clay that marks the end of the Cretaceous and the beginning of the Cenozoic is less than a centimeter thick in most places, a centimeter of clay, separating 66 million years of dinosaur dominance. From 66 million years of mammal dominance, the entire extinction event, the asteroid impact, the darkness, the recovery, the transition compressed into a centimeter of rock. If you could hold it in your hand, you would be holding the most significant transition in the history of vertebrate life in 66 million years. A centimeter thick, the Paleocene-Eocene thermal maximum, the dramatic warming event 56 million years ago, is visible in the rock record as a layer of carbon-rich sediment, rich in the lighter isotope of carbon, the signature of massive carbon release into the atmosphere in a geological instant, a few thousand years of rapid warming preserved in the rock. For anyone who knows how to read it, a message from the deep past saying when carbon rises rapidly, the world warms, the oceans acidify, the deep sea dies, the surface world transforms. The message has been there for 56 million years. We are reading it now in the context of our own rapid carbon release. The rock is trying to tell us something. The animals that changed the world, how individual species altered everything. Some species do not just occupy the world, they transform it. The cyanobacteria transformed the atmosphere, creating the oxygen that makes complex life possible. The first land plants transformed the continents from bare rock to soil and ecosystem. The dinosaurs transformed the structure of terrestrial ecosystems. For 165 million years, the grasses transformed the interiors of continents, and with them the entire trajectory of ungulate and carnivore evolution The beavers transform rivers, creating wetlands that support dozens of species that would not exist without them. The elephants transform savanna into woodland and woodland into savanna by knocking down trees and creating clearings that benefit different species. Elephants are ecosystem engineers, maintaining the specific structure of the African savanna that many other species depend on. Wolves, when reintroduced to Yellowstone in 1995, changed the behavior of elk, which changed the grazing patterns, which allowed riverbank vegetation to recover, which changed the course of rivers. The presence of wolves changed the rivers. Through the behavior of elk, through the growth of vegetation, a trophic cascade, the reverberating effects of a single species through an entire ecosystem. This is what large predators do. This is why they matter. Not just as impressive animals, not just as symbols, but as functional components of ecosystems whose absence changes everything downstream. The intelligence question, again, are we the last or the first? There is a question that the Cenozoic raises that I find impossible to dismiss. In 66 million years of extraordinary mammalian evolution, only one lineage produced something like us, only one lineage. Of all the extraordinary diversity, of all the millions of species that the Cenozoic produced, arrived at the specific combination of large brain and bipedalism and hands and language and culture and the cumulative technological civilization that defines the human species. Was this inevitable, or was it extraordinarily unlikely? Were we bound to arise eventually in any sufficiently long mammalian radiation, or are we an accident, a specific product of a specific lineage in a specific place at a specific time that might easily never have happened? The question matters because it bears on whether intelligence like ours is likely to arise elsewhere in the universe. If it is inevitable, given enough time and enough diversity, then the universe is probably full of minds looking up and wondering as we are. If it is a rare accident, then we may be alone or nearly alone in a universe of 400 billion stars. In a galaxy among hundreds of billions of galaxies, the science does not answer this question. Not yet, perhaps not ever. What the Cenozoic tells us is that complexity is what evolution produces. Given time and energy and ecological space, that brains grow. When brains are useful, that social intelligence is a powerful adaptation in a complex social environment, and that the trajectory of evolution since the Cambrian has been broadly toward greater complexity, greater behavioral flexibility, greater cognitive sophistication, not inevitably, not linearly, but as a general trend over 500 million years of animal evolution, whether that trend would have produced something like us eventually from any starting point, or whether we required precisely this history, precisely this sequence of extinctions and recoveries and climate changes and geographic accidents to exist, is a question that may never be answered. But it is worth asking as you lie here in the world that 66 million years of evolution built for you or not for you, but in which you find yourself nonetheless, the Holocene optimum, the world as it was, let me take you back, not millions of years, only a few thousand, to the Holocene optimum, the warmest period of the current interglacial, about 7,000 to 5,000 years ago, when the world was perhaps 1 to 2 degrees warmer than today in the northern hemisphere. At that time, the Sahara was not a desert. It was a savanna with rivers and lakes, and elephants and giraffes and hippos and people herding cattle, painting on the rocks. The rock art of the Sahara shows a world utterly different from the desert we see today, a green world, a world of water, and animals that the desert has since claimed. The Sahara was green because the monsoon penetrated further north, because the orbital tilt of the Earth was slightly different. The summers slightly warmer in the northern hemisphere, the differential heating between land and ocean slightly greater, drawing the monsoon further into Africa, and the North African grassland flourished for thousands of years before the orbital parameters shifted and the monsoon retreated and the desert returned. The people of the Green Sahara were displaced south into sub-Saharan Africa, north into the Nile Valley, where their descendants perhaps built the first Egyptian civilization on the gifts of the Nile, which was itself fed by the rains of a still wetter African climate. The civilizations we call ancient were built on the climate that no longer exists, in a world that was warmer and wetter in certain place than the world we inhabit now. The insects, the overlooked foundation. I have talked about mammals, about birds, about the great charismatic species, the ones that captured the imagination, the ones in the museum displays. But let me talk about the insects, because the insects are the foundation of almost every terrestrial ecosystem. Without insects, there are no birds, because there's nothing for the birds to eat. Without insects, there are no amphibians. Without insects, there are no freshwater fish. Without insects, most flowering plants cannot reproduce, because most flowering plants depend on insect pollination. Without insects, the nutrient cycle in most terrestrial ecosystems breaks down, because insects are the primary decomposers of organic matter, the creatures that process dead plant and animal material back into the soil that feeds the plants, that feed everything else. The insects are the base, not a decorative component, not an optional extra. The base, and we are losing them. The total mass of flying insects in Germany has declined by more than 75%. In 27 years, in a country with relatively good environmental protections, in a continent with centuries of recorded natural history, 75% gone. In 27 years, similar declines have been documented across the world in every habitat studied with sufficient data. The insects are declining faster than almost any other group, and we are only beginning to understand the consequences. The birds that eat the insects are declining too. The farmland birds of Europe are down 57% since 1980. The populations of monitored butterfly species are down 31%. Since 1990, the chain of consequences from declining insects is running through every ecosystem that depends on them, which is every ecosystem that is not the deep ocean or the open sky. Everything on land, everything in fresh water runs on insects at some level, and the insects are going the ocean story. 66 million years of marine evolution. I focused on the land, but the ocean has its own 6 million year story. A story just as extraordinary, just as full of remarkable creatures, just as shaped by the climate events that defined the Cenozoic. The Paleocene ocean was recovering from the impact, the mass extinction that ended the Cretaceous, devastated the marine world as much as the terrestrial one. The ammonites, those beautiful coiled shell creatures that had filled the Mesozoic oceans, were gone, every last one. The mosasaurs, gone. The plesiosaurs, gone. The marine world was empty in ways it had not been for hundreds of millions of years. And then the recovery, the bony fish, which had survived, diversified explosively into the niches left empty by the extinction. The teleost fish, the group that includes almost all modern fish, from tuna to cod, to salmon to goldfish, to the tiny cleaner wrasses that service coral reefs. All of them are products of this post-extinction diversification. The cartilaginous fish, the sharks and rays, survived as they had survived every previous extinction. The sharks are 450 million years old. As a lineage, they have survived 5 mass extinctions. They were in the ocean before the first forests, before the first reptiles, before the first mammals. The sharks were there in a form recognizably similar to what they are today, and they are still there, still recognizably sharks after 450 million years of change. The most successful vertebrate body plan in the history of the ocean, the coral reefs. The coral reefs, as we know them, are largely a Cenozoic creation. The reef-building corals diversified and expanded in the warm Eocene ocean, creating the complex carbonate structures that we call reefs, the most biodiverse marine ecosystems on Earth, the tropical rainforests of the sea, supporting perhaps 25% of all marine species, despite covering less than 1% of the ocean floor. The Great Barrier Reef, off the coast of Australia, the largest living structure on Earth visible from space, is a Cenozoic creation built up over millions of years of coral growth, layer on layer, each generation of coral building on the skeleton of the generation before, creating a structure of extraordinary complexity and biological richness that took millions of years to build and is now dying in decades as the ocean warms and acidifies. The chemistry that built the reef over millions of years is being reversed. In a century, the great whales, the largest animals that have ever lived. Let me spend a moment with the blue whale, Balaenoptera musculus, the largest animal that has ever lived. On this planet, larger than any dinosaur, larger than any other creature. In 4 billion years of life on Earth, up to 3 meters long. weighing up to 190 tons. The heart of a blue whale is the size of a small car. Its aorta is wide enough for a human being to crawl through. Its tongue weighs as much as an elephant. It can consume 40 million krill. In a single day, a sound produced by a blue whale can travel thousands of kilometers through the ocean. The deepest recorded dive by a sperm whale, a related species, was 2,992 meters into the darkness of the deep ocean to hunt giant squid in the lightless zones far below where any sunlight penetrates. The blue whale is a product of the Cenozoic, of the cooling Miocene ocean, of the Antarctic circumpolar current that created the upwelling of cold, nutrient-rich water that supported the enormous krill populations. That made a krill-filtering whale of this size possible. Without the cooling ocean, without the Antarctic current, without the millions of years of evolution that transformed a wolf-like land mammal into the blue whale. Without all of that, the largest animal that has ever lived would not exist. The blue whale was hunted extensively in the 20th century by industrial whaling, reduced from perhaps 350,000 individuals to fewer than 10,000 by 1966. When it was finally protected, it is recovering slowly as large, long-lived animals do. Perhaps 10,000 to 25,000 blue whales. Now in the ocean, a fraction of what they once were. But recovering, the largest animal that has ever lived is still alive in the ocean right now. As you breathe, as you rest, somewhere in the Pacific or the Atlantic or the Southern Ocean, a blue whale is diving into the darkness or surfacing in the light or singing its low, haunting song into the deep water that carries sound so much farther than air, the soil, the living foundation under every field, under every forest, under every grassland. There is soil, and soil is not just ground up rock. Soil is alive, profoundly, extraordinarily. A teaspoon of healthy soil contains more microorganisms than there are people on Earth. Bacteria, fungi, protozoa, nematodes, mites, springtails, worms, all of them interacting in a web of relationships so complex that we have only begun to map it. The soil food web is the engine of terrestrial life. Plants cannot access most of the nutrients in the soil directly. They access them through the fungi that grow on their roots, the mycorrhizal networks, the wood wide web, as it has been called, connecting the roots of trees through fungal threads that run for kilometers through the soil, transferring nutrients and water and chemical signals between trees, between different species. The forest is not a collection of individual trees. It is a community linked underground by the fungal network that connects them, the old trees, the mother trees, sending carbon and nutrients to the young trees in their shade that cannot photosynthesize enough to sustain themselves through the network, the old feeding the young, the established supporting the emerging, a system of mutual support running through the soil, invisible, essential, ancien. The soil took thousands of years to develop in any given place. Soil formation is slow, perhaps a centimeter of topsoil. In 100 years of biological activity, the deep, rich prairie soils of the American Midwest that made that region the breadbasket of the world were built over 10,000 years of grassland and prairie grass root systems, and the organisms that process those roots into the dark, deep, rich humus that we call topsoil. 10,000 years of biological work to build those soils. Industrial agriculture is eroding them at rates of centimeters per decade. In some places, the work of 10,000 years lost in centuries or decades. The soil remembers the Cenozoic in its structure, in its chemistry, in the organisms that live in it, descended from organisms that have been in the soil for millions of years, building the foundation of life, one dead leaf at a time. The climate archive, what ice cores tell us. In Antarctica and in Greenland, there is ice that has been accumulating layer by layer for hundreds of thousands of years. Each year's snowfall compressed into ice by the weight of the snow above. The oldest Antarctic ice cores extend back 800,000 years, 800,000 years of compressed annual layers, each containing tiny bubbles of air from the atmosphere of that year, each containing chemical signatures of the temperature of that year. The ice cores are a climate archive of extraordinary precision and depth. We can measure the carbon dioxide concentration of the atmosphere in any year for the last 800,000 years from the bubbles trapped in the ice. And what the ice cores show is a striking pattern. For 800,000 years, the carbon dioxide concentration of the atmosphere oscillated between approximately 180 parts per million during glacial periods and approximately 280 parts per million during interglacials, like clockwork, rising and falling, with the cycles of the ice ages never exceeding 300 parts per million. In 800,000 years, the current concentration is over 420 parts per million and rising. It has risen from 280 to over 420 in about 200 years. In 200 years, it has increased by more than it had changed in any previous 10,000-year period. In 800,000 years, the ice is telling us something with great precision and great urgency, that what is happening now is not within the range of what has happened before. In the memory of the ice, the animal minds, what we are learning, one of the most significant scientific developments of the last 50 years has been the discovery that animal minds are richer than we previously assumed. For most of Western scientific history, the working assumption was that consciousness, subjective experience, was unique to human, or at most, present in a very degraded form in our closest relatives, the great apes. That assumption has been demolished by 50 years of careful observation and experiment. Elephants recognize themselves in mirrors, one of the classic tests for self-awareness. They mourn their dead returning to the bones of dead relatives, touching them with their trunks, standing still. In what appears to be reef, dolphins have individual names, signature whistles that function like names that dolphins use to refer to each other. In their absence, when talking about a third dolphin who is not present, this is one of the hallmarks of language, the ability to refer to absent others. Crows plan for the future, hiding food in locations they will visit later, choosing hiding places based on whether they were observed by other crows when they did the hiding, understanding that other crows might steal their cash if they know where it is. Theory of mind, understanding that other individuals, hermins, with different knowledge, different intentions than your own. Octopuses solve problems that no octopus has ever encountered before, using intelligence that cannot be explained by instinct or conditioning, because each individual develops its own strategies through its own experience, in its own lifetime, in a brain distributed through their arms. Unlike any vertebrate brain, an entirely different solution to the problem of intelligence that evolved completely independently. From the vertebrate solution, the animal minds are not empty. They are not simple stimulus response machines. They are aware in ways that we are only beginning to understand and to respect. The last Neanderthal revisited a different kind of loss. I want to come back to the last Neanderthal because I think about them more than I expect to. We talked about them earlier, going extinct around 40,000 years ago, perhaps in the caves of Gibraltar, the last warm refuge of a species that had lived in Europe for 200,000 years. I want to think about what they knew. The last Neanderthals had lived through multiple glacial cycles. Their culture had survived ice age that buried much of Europe in the kilometers of ice. They knew the landscape of Ice Age Europe better than any modern geographer knows any landscape. The caves, the rivers, the migration routes of the animals, the locations of flint, the seasonal patterns of the vegetation, they knew it all in the embodied way that comes from generations of living in a place, of being shaped by a place, until you and the place are not separate. They made music. Perhaps there is evidence of musical instruments in Neanderthal sites. They made jewelry deliberately, with care. They thought about how they appeared to each other, what impression they made, the concerns of any social being with a complex inner life. And then they were gone, not all at once, but one by one, in small groups, in the final refugia, where the hunting was still good enough, and the cold was still manageable, and other humans were not yet present until they were, or until the population became too small to sustain itself. And the last one died alone, or with others, without knowing what they were. The last of the things they knew died with them. The language they spoke, gone. The songs they sang, gone. The stories they told by firelight. In the caves, gone. We carry 1 to 4% of their genome. In our cells, a small inheritance from a vanished world, but the knowledge, the culture, the specific way they understood the Ice Age landscape of Europe is gone, as completely as the mammoths, the current moment, what it means to be here now. You are alive at an extraordinary moment, not extraordinary because it is comfortable, or because it is safe, or because the world is in good order. The world is not in good order. You know this. Extraordinary because of what is possible right now, at this specific moment in the 6 million year story of life after the dinosaurs. You are alive at the moment when the species that inherited the Cenozoic first began to understand fully and clearly what it had inherited and what it was doing with it. The science of ecology is less than 150 years old. As a formal discipline, the understanding of extinction as a permanent, irreversible process is recent. The understanding of the atmosphere as a finite system that can be altered by human activity is recent. The understanding of the deep history of the Earth, the 66 million years of the Cenozoic, the 542 million years of the Phanerozoic, the 4 billion years of life is recent. All of it in the context of human history, brand new. We have had this knowledge for the blink of an eye, and the decisions being made in this blink of an eye will shape what the next 66 million years looks like. The recovery, what is possible. Let me tell you about some things that are happening, because this story is not only lost. The wolves, reintroduced to Yellowstone in 1995, changed the rivers through their effect on elk behavior, which changed the vegetation, which stabilized the riverbanks, which changed the course of the streams, a trophic cascade running from predator to prey behavior to vegetation to hydrology. The wolves made the rivers flow differently by their presence alone, by being what they are and doing what wolves do, the rewilding of large areas of Europe with species that were lost in the Holocene. Bison back in Romania and Poland, beavers back in Scotland and Germany, wild horses back in parts of the Netherlands and France, in Chernobyl, the exclusion zone where humans have not lived since 1986. The wildlife has returned. Wolves, bears, lynx, deer, birds of prey, in numbers not seen in the region for decades. In the absence of humans, the forest is reclaiming the landscape, not because the radiation disappeared. The radiation is still there, but because the human disturbance stopped and nature moved back in. This is not an argument for abandoning cities or for radiation as a conservation tool. It is evidence of something simpler, that life wants to return, that ecosystems, given the chance, given the space, given the time, will rebuild themselves. The great whales, protected since 1966, are recovering slowly, as large, long-lived animals must recover slowly. But recovering, the humpback whale was hunted to near extinction, is now estimated at 135,000 individuals, up from perhaps 15,000 at the low point. The recovery of the humpback whale is one of the most dramatic conservation successes in the history of wildlife management. It took decades. It required international cooperation. It required the willingness to stop doing something profitable for the sake of something that could not pay in any immediate sense, but could pay in the longer term, in the presence of a singing whale, in the spring ocean, as the world recovers from a century of industrial whaling. The songbirds, the living dinosaurs in your garden, step outside on any morning, in any place where something is still alive, and listen. The birds, the wren, that small, explosive, round-bodied bird with the upright tail and the disproportionately loud voice for its size, is a theropod dinosaur, evolved over 66 million years from an ancestor that survived the asteroid impact in some seed-eating, ground-nesting lineage that made it through the darkness and cold of the impact winter and gave rise over millions of years to 10,000 species of living birds, including this one, this small, brown, loud bird singing in the hedge at 5 inches the morning, is a direct descendant of the animals that ruled the Cenozoic for 66 million years. The birds are the living Cenozoic, the most visible, most audible, most daily reminder that the history we have been exploring is not over, is still ongoing, is singing outside your window right now as you breathe. The swift that arrives in summer from Africa, flying at 100 kilometers per hour, eating on the wing, sleeping on the wing, spending years without landing, after fledging until it returns to breed, is the most aerial of all birds, the most fully adapted to a life in the air. It lands only to nest. Everything else happens in the sky, a life spent in the sky from birth to death, almost entirely with the ground as something seen from above, never touched for years. This extraordinary specialization, this complete commitment to a single environment, is the product of millions of years of swift evolution in the Cenozoic, a lineage that found the air and never came back down. If the Cenozoic teaches anything, it is that evolution will find and exploit every possible way of being alive, every possible niche, every possible specialization. Given time, the swifts found the sky, the whales found the deep ocean, the bats found the night air, the moles found the soil, the naked mole rats found the dark, sealed tunnels of East African earth, the life of a superorganism in a sealed chamber with a queen, like insects, but mammals, an extraordinary invention that the Cenozoic tried, and that works extraordinarily well. In its niche, evolution is not done. It is never done. The deep ocean, the world we have barely visited, we have explored less of the deep ocean than we have explored of the surface of the moon. The deep sea floor below 1,000 meters is largely unknown, visited by human eyes. In only the smallest fraction of its extent, what we have seen on the rare occasions when deep-sea submersibles have reached the Hadal zones, the deepest trenches, has been extraordinary life at the bottom of the Mariana Trench, the deepest point on Earth, 11 kilometers below the surface, under pressures that would crush any human technology, not designed to withstand them, under conditions of complete darkness and near freezing temperatures and extraordinary pressure, life, bacteria in extraordinary abundance, amphipods, shrimp-like creatures, in the absolute darkness of the deepest place on earth. Life does not stop at the surface. It goes all the way down into the darkness, into the pressure, into the cold, into every place that physics allows for chemistry to occur. The hydrothermal vents of the deep sea, communities of organisms that do not depend on sunlight at all, that run entirely on chemical energy from the venting of superheated water from the Earth's interior, tube worms 3 meters long with no mouth, no digestive system, fed entirely by the bacteria that live in their tissues and process the hydrogen sulfide from the vent into energy, a complete ecosystem running on chemistry, not sunlight, in the total darkness of the deep sea floor. These ecosystems may be among the most ancient on Earth. Life may have originated at hydrothermal vents 4 billion years ago. The deep sea vents may be the closest thing on modern Earth to the environment where life began. The forests, the lungs of the world. I want to spend a moment with the forests because the forests are not just beautiful, they are functional in ways that our survival depends on. The Amazon rainforest, covering 5.5 million square kilometers, is the largest tropical rainforest on Earth. It contains approximately 10% of all species on Earth. It is home to perhaps 390 billion individual trees, belonging to approximately 16,000 species, and perhaps 2.5 million species of insects, and 40,000 species of plants, and 3,000 species of fish. In its rivers, the biological richness of the Amazon is beyond comprehension. It is the most diverse ecosystem on the surface of the earth. The Amazon also produces a significant fraction of its own rainfall. Through transpiration, the trees release water vapor that rises and condenses into clouds that produce rain that falls back on the forest, that the trees absorb and transpire in a cycle. The forest makes its own weather. The flying rivers, atmospheric streams of moisture generated by the forest, carry water vapor deep into the interior of South America and even beyond, providing rainfall to the agricultural regions of southern Brazil and Argentina that depend on it for their crops. The deforestation of the Amazon disrupts this cycle. Less forest means less transpiration, means less moisture in the atmosphere, means less rainfall. In the agricultural regions that depend on the forest's weather system, the destruction of the Amazon is not just a biodiversity crisis, it is an agricultural crisis in slow motion, affecting the food supply of countries that have so far not made the connection between the forest that is being cut and the rain that is failing to fall on their fields. The forests of the Congo Basin, the second largest tropical forest after the Amazon, the forests of Southeast Asia rapidly disappearing under the pressure of palm oil cultivation and logging. All of them are not just places where interesting species live. Their infrastructure, climate infrastructure, water infrastructure, carbon infrastructure, that took millions of years to build, and that is being dismantled in decades. Sleep, the daily extinction and renewal, every night. You go through a small version of the story we have been telling. You close your eyes, and for a few hours, the ordinary consciousness that makes you who you are dissolves. The sense of self that you have carried all day disperses. The thoughts and concerns and plans and memories that constitute your ordinary waking experience fall into something else, something quieter, older, more fundamental. The sleeping brain is not unconscious, it is differently conscious. The dreams, if you dream, are not nonsense. They are the brain processing, consolidating, integrating the day's experiences into the longer narrative of a life. The hippocampus replaying the day's events to the cortex, transferring short-term memory to long-term storage, the brain doing maintenance that it cannot do while occupied with the demands of waking consciousness. Sleep is not the absence of life. It is the most private form of living, the form where the body takes care of itself without your direction, without your interference, without your conscious involvement, the way the earth takes care of itself without ours. The forest growing, the soil processing, the ocean circulating, the climate regulating, all of it without anyone running it, without anyone making it happen, just physics and chemistry and biology and the deep autonomous self-organizing tendency of complex systems to maintain themselves for as long as conditions allow. The long arc, what 66 million years means for tomorrow, we are at 66 million years in the story that started with the asteroid, with the darkness, with the small, warm, frightened mammals that survived against the odds in the cracks of a broken world 66 million years. From that beginning to this, to you lying here in a room, in a world built from the wreckage of the age of dinosaurs by millions of years of extraordinary biological creativity. And the question that 66 million years of the Cenozoic raises for tomorrow is simpler and fast and impossible to answer with certainty. What do we do with what we have been given? The Cenozoic gave us 10,000 species of birds, 5,500 species of mammals, the tropical rainforests, the coral reefs, the deep ocean ecosystems, the soil microbiomes, the mycorrhizal networks, the great whales, the wolves, the elephants, the vast, patient, self-sustaining machinery of the living world that took 66 million years to build. What we do with it is being decided now, in this generation, in these decades, in these years, not in some distant future, when we will be wiser or better prepared or more capable. Now, with the knowledge we have, with the tools we have, with the will we have, or don't, the 66 million year story does not have a predetermined ending. It has a current direction, and a current direction can be changed. If something changes it, the mammals change direction, after the asteroid, not by choice, but by surviving and filling the space that survival opened. We have a different relationship with change. We can see it coming. We have the data, we have the models, we have the history written in the rock, in the ice, in the genes of every living thing on Earth, telling us precisely what happens when carbon rises, when temperature rises, when species disappear, when ecosystems collapse and recover, and what they recover into, we have 66 million years of evidence about how the Earth responds to rapid change. We know this story better than any previous species has ever known anything about the world they lived in. What we do with that knowledge is the next chapter, the breath before sleep, all of it right here. The breath you are breathing is filled with oxygen, made by photosynthesis over 2 billion years, by cyanobacteria first, then by every plant that has ever grown on every surface that has ever received sunlight. On this planet, the nitrogen in the air is ancient, has been in the atmosphere for billions of years, cycling through organisms, through the soil, through the ocean, through the air, and back in an endless cycle that the biosphere runs without instruction, without oversight, without any mind. Directing it, every breath is your participation in a cycle 4 billion years old. Every breath is your connection to every organism that has ever breathed or photosynthesized or processed nitrogen on this planet. Every breath is the Cenozoic running through you in the oxygen that the last 66 million years of forests put there, in the nitrogen that the bacteria in the soil beneath every tree and every grassland have been fixing for billions of years. You breathe the Cenozoic. With every breath, you are made of it. Every carbon atom in your body was CO2 in the atmosphere before a plant fixed it into organic matter that was eaten or decomposed and cycled again and again through the biosphere before ending up in you for now, for a few decades, before returning to the cycle after you, as it has always returned, after every organism that has ever lived on this extraordinary ancient, still largely mysterious, still largely alive, still regenerating, still full of possibilities that have not yet been tried planet. What comes after the story continues, the 6-7 million year mark will be reached, whether we are there to see it or not, whether the species we call Homo sapiens is still present in some form or has been replaced by something else. The earth will continue, the sun will continue, the physics and chemistry that drive the living world will continue. Life will continue in some form, in many forms, adapted to whatever conditions. The choices of this generation produce for the generations that follow. If the losses continue, if the forests fall, if the coral dies, if the insects decline, if the large mammals go, life will still continue in different forms, in the forms that survive. The rodents, the corvids, the bacteria that have survived everything for billions of years and will survive this too. But the richness, the specific extraordinary richness of the world we have inherited, the one that took 66 million years to build, that richness is not guaranteed. It depends on this chapter, on these decisions, on whether the species that inherited the Cenozoic found a way to be not just successful, but responsible for the world that made them. The sky is still turning outside your window, the same sky that has been turning since before the dinosaurs, since before life, since before the earth. The birds are asleep or singing in the dark, depending on the season. And the latitude, the soil, is alive beneath every surface that is still green. The ocean is circulating its ancien courant, driven by the temperature difference between the warm tropics and the cold poles that the Cenozoic climate built. Everything is continuing. The 6 million year story is not over. It is happening right now in the breath you are taking, in the living world outside your window, in the choices being made by the species that woke up in the Cenozoic and found itself in a world more extraordinary than it had any right to expect, more full of life and complexity and beauty than any law of physics required. A world that worked for 66 million years before anyone was around to notice, and that has been noticed for only the smallest fraction of that time by us, the late arrivals, the inheritors, the ones who get to decide what happens next. Sleep now. The world will still be there. When you wake, older by a night, still turning, still full of whatever it is, full of, still asking the question that 66 million years of the Cenozoic has been building toward. What will you do with all of this? Closing the long breath. So here we are, at the end of 66 million years. We started in darkness, in the months after the asteroid, when the sky was dark and the forests were ash and the giants were gone, and the small creatures crept out of their burrows into a world that had just been remade. And we traveled through the Paleocene, the warm, strange world of the first mammals, the condylarths and multituberculates, and the first primates in the trees, through the Eocene, the warmest world of the Cenozoic, the palm trees at the Arctic, the green Antarctica, the whales making their first journeys into the sea, the basilosaurus, hunting through warm tropical waters, through the Oligocene cooling, the great grasslands spreading, the Paraceratherium, walking through the forests of Asia, the largest land mammal that has ever lived, through the Miocene, the golden age of mammals, the horses evolving on the grasslands, the apes diversifying in the forests, the megalodon, in the deep ocean, through the Pliocene, our ancestors walking upright through the African savanna, through the ice ages, the woolly mammoths, the cave bears, the saber-toothed cats, the world of giants and cold, through the extinctions, the slow emptying of the extraordinary world that the Cenozoic had built, and here till now, to this room, to this body, to this breath, you are the product of all of it, every warm ocean and cold glacier, every primate in a tree, every ancestor who survived when others didn't, every 6 million-year turn of the earth has led to you right here, right now, breathing slowly. In the dark, the condylarths are gone. The Paraceratherium is gone. The Smilodon is gone. The Irish elk is gone. The woolly mammoths are gone. Even the Neanderthals are gone. Except in you, in the 1 to 4% of your DNA that they contributed before they left. But you are here. The latest expression of 66 million years of life rebuilding itself. After the sky fell, let your breathing slow. Let the images settle. The dark world after the asteroid, the warm Eocene forests, the great grasslands, the Ice Age herds, the last mammoth on its Arctic island, and the first humans looking up at the same stars you're lying under right now. The Cenozoic is not over. It is continuing. You are in it right now, one of the Cenozoic mammals, resting at the end of a day on a planet that has been doing this for 66 million years and will keep doing it long after any of us can imagine. Close your eyes. The world has survived worse, and the small creatures with warm blood and large eyes who hid in the dark when the sky fell are still here, changed beyond recognition, but still here, still curious, still alive, still wondering what comes next. Rest now. The Cenozoic is still going. It can wait until morning